Finish up our notes on section 4.4. We're going to look at a couple more complicated examples of drawing a graph and identifying the components of sine and cosine graphs, and then we'll also look at an application of one. So first, let's do another example where they ask you for the period and the amplitude. So the period we talked about yesterday comes from doing the value 2 pi divided by b. Now in this case, my b value is the fraction 2/3. So for my period, I need to be able to say 2 pi divided by 2/3, but instead of having a fraction divided by a fraction, we find that easier to evaluate as 2 pi times the reciprocal of what's in the bottom. So I'm basically doing keep, change, flip. So 2 pi times 3/2 instead. And then in this case, the 2's will cancel out, so the answer is 3 pi. Second, we talked about the amplitude. The amplitude comes from the value that's out front of the function being multiplied. So make sure you take the absolute value of it, but in this case, our amplitude is just going to be 4. Now, what these two numbers mean for us graphically, the period is telling us how long of a distance it takes horizontally for the graph to go through one complete cycle. And I can see one complete cycle starting from here at the origin, going all the way to the top, all the way down to the bottom, and then back to this point at the line y equals 0. So right here, it's hitting y equals 0, going from the negative side to the positive side. And that's the same place we were at when we started. It was hitting a height of y equals 0, and it was going from the negative side to the positive side. So it was increasing through here. So that means that this whole length, this horizontal distance across for that one cycle, is a distance of 3 pi. So instead of marking off using units like 1, 2, and 3 for our tick marks, I would probably be marking this off as 1 pi, 2 pi, 3 pi, just to make it easier to graph. So now I know what the horizontal distance is for one complete cycle. Second, we know that the amplitude is how high the graph is reaching. So the amplitude is just half the distance from the top to the bottom, or it's the distance from halfway through the graph to the top, or from halfway through the graph to the bottom. So now I know the heights of this graph. When they say give the viewing window, they just want to know what the x and y dimensions are for the shown graph in here. They basically just want us to say how far across is it and how tall is it completely. So for the viewing window, usually we have two setup values. We have one interval for all of the x's we see, and then one interval for all of the y's. So for the x's, we said it's going to a positive length of 3 pi, and it must be doing the same thing in this direction as well. Starting from 0 and going to the left, that must be 3 pi in this direction. So my viewing window would be all the x values from negative 3 pi to positive 3 pi. And then for the y coordinates, I'm also going to specify an interval. How far up and down on the graph are we seeing right here, as if this was our graphing calculator window. So the lowest point the graph is reaching is -4, and the highest point the graph is reaching is +4. So the viewing window for the y values is all of the numbers from -4 to 4. And remember, the reason I'm using this square bracket is because I'm saying we do include the endpoints. This is what we called interval notation. So I'm saying all the numbers from -3 pi, including that endpoint, all the way up to +3 pi, including that endpoint. We're just specifying which numbers we see, all of the ones in between. Now let's talk about finding the maximum and minimum values of a graph. And you want to be able to do this both algebraically, from working out the equation, and from looking at a graph graphically as well. So we'll look at both of those separately, make sure you're comfortable with both processes. Now algebraically, what we just saw on the last slide was that the amplitude describes how high and low the graph reaches. Well, that's what's going to determine our maximum and minimum values. The maximum would be the highest point the graph ever reaches, the minimum would be the lowest point the graph ever reaches. And that value comes from our amplitude. So if I was to do this algebraically, instead of from having the graph on hand, if all I had was the equation, I would need to figure out the amplitude of the graph, and in this case, the absolute value of -1 is still a +1, because I don't have another number out front, like a 2 or a 3 or a 4. So that means the highest my graph is ever going to reach is positive 1, and the lowest my graph is ever going to reach is negative 1. So I can now say that the max, the highest point will be 1, and the minimum value will be negative 1, since that's the distance from halfway through the graph to the top or from halfway to the bottom. So the highest point is going up, the lowest point is going down. So algebraically, we've just found the maximums and the minimums. To find the zeros, it's important to know where the zeros of the regular cosine of x graph are. And we talked about this a little bit when we were drawing the graphs yesterday. We said that the standard cosine of x graph starts at a height of 0, 1, and then it goes down to this point. So that would be a 0 at pi over 2. Then it comes down to pi, and then it comes back to 3 pi over 2. And it keeps going through this pattern. And do notice that on my scale, I'm using this height as 1. So that means each tick mark is actually a 1/2 for what I'm setting here on my scale. So it's important to know that the zeros of the regular cosine of x graph occur here at negative 3 pi over 2, here at negative pi over 2, pi over 2, and 3 pi over 2. So we have 4 zeros that we usually look at in the interval from negative 2 pi to 2 pi. Now the difference for this particular equation is that my graph is being stretched out. The b value is 1/2, and so your period is 2 pi divided by b, so it means it's actually 4 pi. So this is doubling the height of everything in the graph. So I need to take those zeros and multiply all of them by 2, because they're also going to be stretched out. They're going to be twice as far as they normally are. So use the horizontal stretch or compression and apply that to the zeros of the standard graph. So in this case, I'm going to multiply my zeros by 2. So now I'm going to have pi over 2 times 2, 3 pi over 2 times 2, negative pi over 2 times 2, and negative 3 pi over 2 times 2. So those are the zeros for our stretched out graph. We doubled the distance for the zeros just like we doubled the period of the graph. Now, it is also nice if you can do these graphically, so it helps if you can just draw the sketch and then look at where it is actually touching the x-axis for reference. So we could have done that instead. I already put in the dots for where the regular cosine of x graph would be, and then now if I'm applying our transformation rules to them, we want to notice that there are 2 different transformations being applied to cosine of x. The first one is just taking the dots we have and flipping them upside down around the x-axis. And the second one is having the x value divided by 2. That's doubling the length of everything horizontally. So instead of having this dot here, I'm going to double that length and put it somewhere on the pi line. So for the first dot, this one's already on the y-axis, so it's not going to have any of the doubling distance from the value of 0. It's still going to be on this line, but I do need to flip it upside down. For the next dot, that needs to be doubled out in length. So I'm paying attention to this dot, but I'm shifting it out to pi. And then for the flipping it upside down part, that's not going to come into play here because it's already at a height of 0. So flipping it around the x-axis isn't going to cause it to move anywhere. So this dot is just being doubled out in length. This next dot was normally at pi, but now it's being doubled out. So I'm actually going to be looking at what it's doing for 2 pi. And the second thing I need to do for it is I need to flip it upside down because of the negative out front. So this dot should be moved out to the 2 pi x value, and then it needs to be flipped upside down. So now I have the start of what the graph is doing here. The same thing would be happening on this side. I would be taking the negative pi over 2 dot. I'd be doubling it out to negative pi for the horizontal stretch, and then I would be flipping it upside down, which doesn't affect anything here, so it stays at a height of 0. The next dot, I'm doubling out its horizontal distance, and then I'm flipping it upside down. So here's what's happening on the left-hand side of the graph for the negative 2 pi to 0 part. And so if I had given you this graph, I hope that you would have been able to recognize that the highest point the graph ever reaches is a height of 1, the lowest point the graph ever reaches is a height of negative 1, and that the zeros Now I can only actually see the zeros of pi and negative pi on here. In fact, since this specified from negative 2 pi to 2 pi, we didn't even have to worry about these two answers. That's where our zeros normally would have occurred, but they ended up outside of the interval. So all we actually needed to pay attention to were negative pi and pi. For this last example of identifying the different components, we just have one ugly one that has all four different values, A, B, C, and D filled in. So we just want to be careful about applying them one at a time. It's uncommon to have one with all four of the shifts. So the amplitude that comes from the absolute value of the number out front, the answer to that is going to be 2. The period is 2 pi divided by B, and in this case, B is a 2. So I'm going to have 2 pi. For sine and cosine, it's always 2 pi on top of b, and then make sure you reduce the fraction, whatever you get out of it. So in this case, the period is just pi. So now I know it will complete one full cycle in a span of pi instead of the normal 2 pi span. Next, we have our phase shift. And for this value, it's c divided by b. So we're going to have negative pi over 2 divided by 2. And again, instead of having a fraction divided by a fraction, it's easier to think of this as multiplying by the reciprocal. So negative pi over 2 times 1/2 instead. So we're actually getting a phase shift of negative pi over 4. And what we showed in the notes was that if this value is negative, then it's actually shifting that pi over 4 distance to the right. So it's important to recognize that this is actually shifting the graph to the right instead of the left, which often confuses people because of the sign. And the last piece is the vertical translation. For the vertical translation, we're looking at the value d. This is showing us how far the graph is being shifted up or down. So this one is being shifted down 1. So I would just specify something to say that it's going down a length of 1. So sine and cosine graphs actually have a variety of applications. They're useful for anything that has some kind of a periodic pattern to it. For example, describing high and low tides, or even simple systems like your inhaling and exhaling, how full your lungs are with air at a given time. So anytime you have something that's going through a repeating pattern, you can use a sine or a cosine graph to describe its motion. In this specific application, I'm going to draw a rough sketch of this so that it makes it easier for me to identify where the patient's lungs would be full or empty of air in the interval from 0 to 2 pi. Now, the numbers might be saying 0 to 2 pi, but would actually be more useful for us to think of them medically as something like how many seconds have gone by or how many minutes have gone by, something to that effect. And the value of 1 would be saying like 100% full, and the value of 0 would be the lungs are completely empty. So that's what we would be thinking about with our scale, even though we're still seeing numbers like pi over 2, pi, 3 pi over 2. You would just have to think about what the units might be referring to. So we're only going to look at the 0 to 2 pi side of the graph, and this is based on the sine function. So it's important to remember that the normal sine function passes through these particular dots. And again, I'm setting my scale so that 2 tick marks is equal to 1 unit. So then 2 tick marks down is negative 1. And then my x-axis is already labeled here. So there are a few translations happening. One of the translations is that the height of the graph is being cut in half. So now I know it's not going to be going up 2 tick marks and down 2 tick marks. It's just going to be going up 1 tick mark and down 1 tick mark. Second, we have a 2 in here being multiplied by the t value, or x is usually there. So this is going to have the effect of compressing the graph. So everything is going to be half as far out as it used to be. So if it was 2 tick marks out, it'll be 1 tick mark out. 4 tick marks out will be 2 tick marks out, etc. So this is going to cut the horizontal distance in half. And then we're also going to shift all of those heights vertically a unit of 1/2. So starting from this first dot, I don't have to worry about doubling its horizontal distance out because it's at a distance of 0, so it doesn't affect anything. I also don't have to worry about multiplying the height by 1/2 because 0 times 1/2 is still 0, but I do need to shift it up 1/2. So that dot ends up in this location. My next dot here at a height of 1 normally, this one is going to be cut in half, so it's going to move to the first tick mark horizontally. I'm going to cut the height in half, So from a height of 1, it's going to go down to a height of 1/2. But then I'm going to go back and add 1/2 to the height. So it actually ends up back at this height anyways. For the next dot, I'm cutting the horizontal distance in half. Then I'm multiplying the vertical distance by 1/2, which doesn't affect anything because it's a height of 0. And then I'm adding 1/2 to it. Next, I'm taking this one, which was 1, 2, 3, 4, 5, 6 units out. Now it's going to be 3 units out horizontally. I'm cutting the length in half, and then I'm adding 1/2. So the horizontal got cut in half, the vertical got cut in half, and then I added 1/2. So once you have a few of the dots drawn, you can actually just go through and say, okay, everywhere in between going through this pattern, it's just going to keep going through because we have one full period of it now. So now I know it's going to keep going up, hit this point and bounce off, and then down, hit this point and bounce off. So I don't have to keep going through and doing the dots one at a time. As soon as you have one full period, you should be able to pretty well see the motion of the graph. And then the question asked, what are the times where the patient's lungs are full? Well, that would be happening here where it hits a height of 1. So that was the half of pi over 2 value, which would be pi over 4. So full lungs is occurring at pi over 4. And then it's happening again at this point, which would be pi over 4, since each tick mark is 1 pi over 4. So 1, 2, 3, 4, 5 pi over 4 is the second place where we see the full lungs. For where the lungs are empty, we also have 2 locations for that. We have one of them located right here in the graph, and so that's 1, 2, 3 pi over 4. And then we have a second location for this happening out here at 1, 2, 3, 4, 5, 6, 7 pi over 4. So that was just to show you an application of where you could apply something like this in your life, especially in a medical field. And again, remember that you're thinking of these values as referring to something like time. So maybe it's referring to how many seconds it takes for them to hit this point and then to go back through the entire breathing cycle. That's all for the notes today. Thank you.